Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. And in today's lecture, we will be seeing three-phase half-wave converters with R load. And if you see, here R phase is being connected to thyristor 1, Y phase is connected to thyristor 2, and B phase is connected to thyristor 3. And here load other terminal is connected to neutral. And here the supply voltage is three phase. Previously we have seen single phase semi converters as well as full converters, and the reason why we are going for three phase converters is in order to meet higher rating applications we need to obviously go for three phase supply. And here three phase supply, I'll teach you how to draw these waveforms. If it is graph or even if it is in notebook, this is how you need to draw the waveforms. See, indicate dot for every 1 centimeter. If you have got a graph, that is fine, or otherwise you need to keep dot for each centimeter. And now let me draw the phasor diagram for R phase, and it looks like this. This is for R phase, and if we need to draw the waveform for Y phase, see, here it will be 120 degrees phase shifted. So here, if you name this as 0, 60, 120, 180, 240, 300 and 360. See, here R phase will be starting at 120 degrees. This is because Y phase will be lagging behind R phase by 120 degrees. So that is the reason. And then B phase, if you see B phase, it will be lagging behind Y phase by 120 degrees and R phase by 240 degrees. So that is the reason here waveform starts 250. I am connecting this to back end because we never know where the waveform starts, which is continuously moving. And if you need to draw in graph, see, take this scale as 1.5 centimeters and each 60 degrees is equal to 1 centimeter. In that case, it will be easy. Or otherwise, even if it is in notebook, we can draw like this. Alright. So here, this is the phasor diagram where R here is taken as reference. This is R as a reference, and Y phase, it will be 120 degrees apart. That is Y phase. If you see even in this diagram, Y phase is lagging behind R phase by 120 degrees, and here B phase is lagging behind Y phase by 120 degrees. And again, B phase is phase shifted with R phase by 120 degrees. So all the three phases are 120 degrees apart. And here, if you see, this is the zero crossing. This is the zero crossing. So until this point, even if you provide the triggering pulse, thyristor will not be able to conduct. The moment it reaches zero crossing, after exceeding this zero crossing, we can provide the triggering pulse, whichever is forward biased. And if you see right from this zero crossing, R phase is more dominant. R phase has been started. So, if we can provide the triggering pulse for thyristor 1, it starts conducting. And we need to choose the firing angle such that it need to exceed this zero crossing. And this zero crossing is occurring at the instant called pi by 6. Is it not? Pi by 6. What is pi by 6? 180 by 6. That is 30 degrees. And beyond which we need to provide the triggering pulse. That is at the instant called pi by 6 plus alpha. Let me take alpha is equal to 30 degrees. So here at this instant called 60, our thyristor starts conducting. If at all, if we can provide the triggering pulse for thyristor 1, because R phase is being appeared. So here I am providing the triggering pulse. This is pi by 6 zero crossing, and alpha is equal to, I have chosen such that it is 30 degrees. So this is the triggering pulse for the width till pi. So that is the reason from pi by 6 plus alpha, thyristor 1 is conducting till pi, till this instant called pi. And if you see, Y phase has been appeared, but thyristor 2 doesn't conduct because we are not providing any triggering pulse for the thyristor 2. So that is the reason. And if you see, I am calling this instant as pi, and if you check out, I have written this as 5 pi by 6 plus alpha. Why is it so? See, pi by 6 is pi by 6, 180 by 6 is 30, 30 into 5, 150, 150 plus alpha. Alpha we have taken it as 30 degrees. So 150 plus 30 degrees is equal to 180 degrees. So thyristor will be conducting till this instant called 180 degrees. And once it reaches 180 degrees, what happens? See, thyristor 1 will be getting turned off because Y phase has been appeared, and this thyristor 1 will be reverse bias, and the moment at this instant zero crossing, exceeding zero crossing, that is at this instant called 5 pi by 6 plus alpha, I am providing the triggering pulse for the thyristor 2, and that is how thyristor 2 started conduction, and that is conducting from 5 pi plus alpha to 2 pi. And now here at this instant thyristor 2 is conducting, and the moment it reaches, see, as long as Y phase is present, thyristor 2 is conducting, and once the negative half cycle has been appeared, thyristor 2 is reverse biased and turned off, and at this zero crossing, exceeding this zero crossing at this particular instant called alpha, if I am providing the triggering pulse for the thyristor 3, in that case thyristor 3 conducts, and it starts conducting from this instant and till here as long as B phase is supplied. And the moment B phase turns negative, T3 is reverse bias and it stops conduction. So this is nothing but your output voltage waveform for 3-phase half wave converter with R load. And now talking about the output current, as we have already discussed, since this is resistive load, I naught is equal to V naught by R. So the output waveform will be one and the same. Only thing, I naught will be reduced by a little when compared to that of the output voltage. So your output current is present right from pi by 6 plus alpha to pi. Alright, so this is your output current, and now output current waveform is just similar to that of the output voltage, and this is I naught. Now taking alpha is equal to 60 degrees. Previously we have seen for output voltage for alpha is equal to 30, and now let us take alpha is equal to 60. See here, this is zero crossing. If at all, if we are taking alpha is equal to 30, it started conducting from here, and if at all alpha is equal to 60, in that case it will be conducting right from here. So at this instant called 90, since we are providing the triggering pulse, that is pi by 6 plus alpha, pi by 6 plus alpha in the sense 60, this is already 30. So at this instant called 90 degrees on scale, our thyristor 1 will be conducting because R phase supply is being appeared. So R is connected to thyristor 1. Thyristor 1 starts conducting current through the load until this instant called pi. Once it reaches pi, thyristor 1, see, R phase will be going negative. It makes thyristor 1 reverse bias, and that is how thyristor 1 gets turned off at this instant called pi, and now it remains 0. since we haven't provided any triggering pulse for the Y-phase thyristor, that is thyristor 2, and at this instant called 5 pi by 6 plus alpha, now I am providing the triggering pulse for the Y-phase. See, Y-phase triggering pulse is being provided, and that is how here T2 is conducting, and it is conducting as long Y-phase is positive. Once it turns negative, T2 is turned off, and again here D phase is being appeared, and at this instant called pi by 6 plus alpha, alpha is equal to 60 degrees, that is on scale 90 degrees. Thyristor 3 starts conducting because of the B phase polarity. And this is how the thyristors conduct, and we get the output voltage as well as output current waveforms. And let us check out the V0 average expression for 3-phase half-wave converters with R load. And here V0 average, the general formula is 1 by T, 0 to T, V0 of omega T, d omega T. And here if you see time period, let us check out the waveform. Here time period is every cycle is repeating for 120 degrees. 120 degrees in the sense 2 pi by 3. Every similar cycle is repeating for 120 degrees. Each thyristor is conducting for a period of 120 degrees. That is, this is 60 and this is 60, 120 degrees. So that is the reason here time period will be taken as 2 pi by 3. That is 120 degrees. For every 120 degrees, a similar cycle is repeating. So that is the reason 2 pi by 3. And it is actually conducting from. So what are the limits? Here limits are, see, pi by 6 plus alpha to, it is conducting till 5 pi by 6 plus alpha. Is it not? So that is the reason here limits are pi by 6 plus alpha till 5 pi by 6 plus alpha, where V0 is equal to Vm sin omega t d omega t. And taking this 3 up, bringing out Vm, 3 Vm by 2 pi, integration of, that is, integration of sin omega t is minus cos omega t within the limits pi by 6 plus alpha to 5 pi by 6 plus alpha. And if you substitute the limits, upper limit minus lower limit, that is, we get the final expression for V0 average as 3 root 3 Vm by 2 pi cos alpha. This is the final V0 average expression for 3-phase half-wave converter with R load. Similarly, let us check out the expression for VRMS. V0 RMS is equal to, the general formula we have is 1 by T, 0 to T, V0 of omega T, V0 square of omega T, d omega T, whole to the power of 1 by 2. Here time period is, every similar cycle is repeating for 2 pi by 3, 120 degrees. Again, limits are conducting from pi by 6 plus alpha to 5 pi by 6 plus alpha Vm square sin square omega t d omega t whole to the power of 1 by 2. And if we resolve this expression, 3 Vm square by 2 pi, and integration, in order to integrate, we need to write this sign in terms of cos 1 minus cos 2 omega t by 2 whole to the power of 1 by 2. In that case, we get V0 RMS expression as Vm under root 1 plus 3 root 3 by 8 pi into cos 2 alpha. This is the final V0 RMS expression for 3-phase half-wave converter with R load. In the upcoming lecture, we'll see 3-phase semi-converter with RL load. Thank you.